Um, I think we can get started. The time is 6:05. We already have 10 people joined in the WebEx. We have around 22 registrations till now, Nasir. So we are hoping some more people will join. Um, and yeah, so today's webinar is about eye movement and programming. Um, so just wanted to give a little bit of introduction. I am the Secretary of Computer Society and Computational Intelligence Society of Schenectady. Um, and we are doing this in the collaboration of the two chapters that I mentioned, Computer Society and Computational Intelligence Society of Schenectady section. This is the second webinar that we are having. We started last month and we had very good response for the in-person webinar, and this is the virtual webinar. This is the first webinar that we are doing this year. And about IEEE Schenectady section, this has very rich history and it's one of the earliest section of IEEE. It is established somewhere in 1900s, and this section has pretty large history, more than 100 years, I believe. We have so many IEEE people, so many professionals around this area, and I believe we also have a Nobel laureate from one of our IEEE section members. So it's a great thing that we are connecting together and discussing all these new technical advancements around our area, and also this event is also part of the IEEE Day. So IEEE Day is a global event that is celebrated all over the world, and it actually is the first Tuesday of October. So October 2nd, October 7th will be the first Tuesday. So this event is also part of that. So we will be leveraging the IEEE Day theme, which is leveraging technology for a better tomorrow. And we have our speaker, Dr. Naser Al Madi. He is an assistant professor of computer science in Colby College, and he is presenting this topic on eye movement in reading and programming. So I hope everybody would be really interested, and the questions will be taken at the end. I'll be muting all the participants at the end of the section. We'll have, I think, 15 minutes of Q&A. We have this WebEx meeting going from 6 to 8. The WebEx, the webinar is from 6 to 7. 5, 10, 20 minutes here and there also should be fine. And then now I hand it over to Dr. Nasir to start his presentation and share his research. Thank you.
John, I hope you can hear me. I appreciate the kind introduction and the invitation to talk to you about my research at the IEEE Schenectady chapter. So I prepared a few topics to share with you all, and I hope that we'll have a little bit of an interactive part in the beginning. So maybe you would be able to either respond in the chat or unmute yourself and possibly respond. So, my research in general revolves around the idea of studying eye movement through eye tracking in reading in general and in reading source code in particular. So, I have three projects that I will go over on a somewhat high level, and I'm happy to go into the details throughout the Q&A. So maybe a dramatic introduction, but I want to talk about the greatest human invention, or possibly something that we could argue is the greatest human invention, which Carl Sagan described as basically reading, the ability to read, perhaps the greatest human invention, binding to other people who never knew each other, allowing one person to be inside the mind of another, maybe somebody who's been dead for thousands of years. If we think about it on a level, our ability to create basically written language specifically allowed us to transfer our knowledge through the generations and build the civilizations that we have today. So the study of reading and writing is of great importance, especially in the context of modern artificial languages that we've created that we call programming languages. So the foundational idea that I hope if we get one idea from this talk today, it would be that there is a connection between linguistic factors and human cognition. So there's a link between eye movement during reading and what's going on inside the human brain. And to just affirm this idea, I prepared a very quick introduction that we could possibly test ourselves. But three factors basically control this connection. among many others. Three are very popular and discussed a lot and studied a lot in the literature. So here is basically an eye tracker. It's a device that tells us where a person is looking at on a computer screen. And it basically, some of these common models are camera based, and they take about 1,000 frames per second. And they have a really good spatial and temporal accuracy that it makes them reliable enough for use in reading research specifically. We look at eye movement in terms of two main movements. So these are fixations where the eyes stay momentarily over a word, and this is where we extract information, and the jumps between these words are called saccades. And basically, we do not extract information during saccades. This eye movement also, the duration of the fixation, how long we stay stationary on a word, is correlated with the nature of that word. And that's a very important fact. And maybe I'm foreshadowing here a little bit, but we're going to skip about 20% of the words. So in English readers, on average, we skip 20% of the words. We actually do not fixate on them for one reason or another that I'm going to discuss later on. So one of the most important effects is the word length effect. So we find that the longer that word is in terms of number of characters, the longer that we will fixate on it in milliseconds. And we noticed that the duration is something like 150 milliseconds. So it's actually, eye movement is very intricate, it's very quick. So we kind of get the illusion of very smoothly moving when we're reading over a line of text, but actually that involves a lot of jumping around. So the word frequency effect is more interesting than the word length. Length is purely the longer the word, more time we're going to need to extract information. It's kind of understandable. Word frequency is based on the fact that we have neural networks in our brains that become better trained as more they see certain stimuli or certain words. We become more able to find out their meaning and their pronunciation quicker. So the duration of time we fixate on high frequency words is lower. Just for the sake of testing this, so we would kind of, to a certain unofficial or maybe informal level, we agree on the fact that eye movement has something to do with cognition. I will show you a question and I want you to answer it as soon as possible. So I'm going to give you a few seconds. We'll go over the answer together, but please be ready. All right, here we go. All right, I cannot see you, and I know this is virtual, so I'm going to jump into the answer, and hopefully you are either searching still for the mistake or you found it already. The mistake is that we have duplication of the word the, and this is specially designed basically text where we have the word the as the most frequent word in the English language, and we place it here after a return sweep, which is a position where we are likely to make mistakes and our brains are prepared for us to either overshoot and undershoot or read something twice or miss something. And also it's very predictable in that context, so our brains are efficient in the way that they read, that they decided that mistake is not going to be noticeable. And also I distracted you with colorful numbers at the bottom. And I also told you to do it as quickly as possible. But the point that we're trying to make here is that we can actually predict the amount of time you're going to spend on words based on the nature of these words and their position in the text. And the word frequency effect describes basically this as basically, I'm going to jump to the next figure. The higher the frequency of the word, such as the word da, we'll spend less time on it. Less frequent words, such as the word sip, that is equal in length, 3 letters, but it's rarely appears in the English language, less than 100 per million words. We actually will spend about 150 milliseconds more on a word in the same position that we only vary its frequency. Frequency is not dependent on the context. We can get it from a database that analyzes a lot of text in English and determines that in every million words, we found the word 65,000 times or approximately 65,000 times. And that is often updated because our way of using language changes. Something is a little bit more dependent on context is predictability, where more predictable words take less time to be processed and fully analyzed by our visual system because we do something called top-down processing, where our comprehension tells eye movement, I actually know the next word. We don't need to fixate on it. We can be more efficient. We can read faster. Let's skip it. And just for the sake of another experiment, informally, I'm going to give you a sentence and I will give you a few seconds to tell me the missing word. If anybody would like to mute and tell us the answer, that would be awesome.
Liver.
Liver, excellent. So liver is a highly predictable word in this context, and it's highly skippable. So people will actually not fixate on it. So not only we can predict with a certain level of accuracy what will be skipped and what will be actually fixated, we can also predict the duration of the fixation on the word based on its length, frequency, and predictability. So we can actually build models of eye movement control for reading something in natural language. I want to start with a project that focuses on natural language, or something that we do a lot. So one of the recent projects that I worked on with two of my collaborators was about actually finding a better way to read. It's like a big question. You might have heard about techniques such as speed reading, where people kind of fixate in the middle of the page and they try to extract information quickly by reading books in like 10, 15 minutes that would take weeks to actually read word by word. Or we could call this pattern of typical normal reading linear reading. And this is how educated people are trained to read, and this is how we actually, all of us, to a great extent, read natural language. Unfortunately, speed reading, despite its popularity throughout time, and there are some times that the topic keeps coming back, there aren't any scientific experiments that prove that speed reading in particular is actually a good technique, that we could actually get a good level of comprehension through speed reading. But there are many techniques that are often studied for better ways to read, which would allow us to read faster or with higher concentration or attention, or perform better in comprehension tests. One example of this that is very popular on the internet is called bionic reading, which I have a snippet of here. This technique, basically, a lot of people on the internet say that it helps them with attention deficit problems. Again, not a lot of studies actually confirm this idea, but these are some of the ideas of trying to read faster or with better attention. That not necessarily there are a lot of evidence for them scientifically through a controlled scientific experiment. My collaborators and I worked on an idea where two of my collaborators actually created a technique for reading called GPTSM. And we conducted an eye tracking study to see, does it actually work? And I'm going to share the results of the project with you. So here is a typical text that is usually given for something like the GRE exam, where people would read a snippet of text and they are asked some comprehension question about it. So this is, we could call it the controlled group or the plain interface, where people are expected to read in the linear pattern that we've covered before. With the GPTSM interface, it uses large language models in the back in a recursive process of de-emphasizing less important text. And unlike summaries where we remove sentences or we rewrite the text in a shorter form for people to read it, GPTSM is creative in the way that it actually maintains the grammatical correctness of the sentence. So I'm going to read a sentence with you and we can notice this together. So if I read only the highlighted or the emphasized part, it's going to be grammatically correct. So the Galileo spacecraft captured data about Jupiter's atmosphere that challenged theories about Jupiter's structure. And as you can tell, that sentence was actually grammatically correct. We didn't have a grammatical disconnection in the middle of it. At the same time, this way allowed me to actually explore other details if I felt like I needed. And more importantly, it maintained the structure of the text. And that seems to be important on a cognitive level. So we find information in a certain page, the location of that information relates to how we remember it. So it maintains the original structure and it gives us 4 or 5 levels of de-emphasizing the text to allow us to read faster, yet we are able to explore a little bit more beyond what is highlighted if we felt like we need more information to understand that sentence or that structure. So with this technique comes 2 important questions. Does it actually work? Are people guided by this highlighting? And the second question, how do they do in comprehension tests? So are they performing similar? If they read faster, but they perform similar to the control group, that would be awesome because for the first time we would have a technique that has an advantage in basically reading aid or a better way to read. So with eye tracking, we're actually able to answer these questions. Here I'm comparing the same text that we just looked at. And on the right, we can see the linear reading pattern for a normal text, the control group, the paragraph, that basically we can see the fixation and the skipping patterns that we've discussed before. And also we can see on the GPT-SM interface that people are actually guided by, at least this participant is guided by the highlighting and de-emphasizing. Yet at the same time, they actually explore sometimes things that are not necessarily highlighted or emphasized. So they read parts of the de-emphasized side. So the second question is, are people actually spending time in milliseconds that is correlated with the level of emphasizing and de-emphasizing? Here are the five levels of basically de-emphasizing the text. 0 means that the text is fully dark, just normal text, and 4 is the most faint and least highlighted text. So when we look at three metrics, first fixation duration, gaze duration, and total time, that describe different phases of the lexical processing of words and how much basically we refixate on a word. Sometimes we jump back to it to spend more time on it. So total time includes that, while first fixation duration is just purely the first fixation. We can see on all three metrics that people are actually spending more time on the highlighted part and less time on the de-emphasized part, meaning that the technique was actually successful in guiding eye movement for participants. Possibly the most interesting fact about this project is that not only people read faster, of course they read faster because they had to read less, but they performed slightly better, not on a statistically significant level, but slightly better above the control group on comprehension questions, which is really fascinating because usually any fast reading technique will immediately have a negative effect on comprehension. So this is one idea on natural language, and it combines basically the use of eye tracking with the idea of creating new interfaces that would help with reading. Eye movement in programming in particular is a significantly different problem, so let me tell you why, and why it's really important to study eye movement in programming. So research shows us there are so many papers that tell us that actually programmers spend 60 to 80% of their time reading different pieces of code and less percentage actually writing. So whether we are actually creating automated tools to help people with generating code or writing code, that is less significant than helping them with the reading code. And programmers spend that time either comprehending the code, just so they would understand it. They are reading it to modify it, to debug it, to review it, all kinds of realistic, basically reading behavior. And now you're going to start noticing it. If you look at your schedule, you're going to probably notice that you read a lot more than you write. The second extremely important fact that relates to basically reading and source code in particular is that finding and fixing bugs later on is extremely more expensive. If we find bugs during requirement gathering and architecture, it's really actually cheap and quick to fix these problems. If we do it during coding, that's also still very cheap. But after that, the percentage of basically cost becomes exponential. So we spend 30 times more to find a bug if the bug actually is discovered in production. So we have a motivation to try and find bugs early on during the coding process. And putting that in the context of large language models and automated way of generating code, we automatically start asking the question, how often or how readable is model generated code? So in another project that was done early on when something like GitHub Copilot first made an appearance and was advertised as an AI pair programmer, we thought about how are people using it and to what level are they inspecting the suggested code. So as you know, pair programming is a technique that matches two programmers together to work collaboratively on a piece of code. And they switch between two roles: the driver, who has their hands on the keyboard and mouse, and they are the actual person who will type the actual code, and the navigator, who is going to take more of an observing role and is going to look at the overall structure and suggest and try to critically think about defects and structural issues. So several studies have examined AI-generated code, yet we don't know a lot about, at least at the time of working on this project in 2022, we didn't know a lot about the readability of model-generated code. So there's a possibility that, especially in the beginning of the AI-generated code era, that there is a certain level of automation bias where programmers check the generated code a couple of times, then they realize, oh, it's actually pretty good, and they stop actually inspecting it, and they would start accepting it, which would lead to bugs that are discovered in the latent stage of software development, where it's extremely expensive to actually fix it. So in the project, we focused on two ideas: code readability, how readable, how similar is AI generated code to code written by human pair programmers, and also the visual inspection of the code as we would observe it from eye tracking. So we've modified our lab to capture basically the eye movement of a participant and also allow somebody else to pair program with them through another set of screen and keyboard. The participant, of course, alternated between the role of driver and navigator, and then on an equal duration session, they collaborated with GitHub Copilot. And we recorded their eye movement through the 3 tasks that they've completed, and we also collected the source code that they wrote in each one of the tasks. We had to create an a specialized tool to do eye tracking in VS Code, because at the time of doing this research, GitHub Copilot was only available in VS Code. I know it's not the case anymore. And also, VS Code was not supported by the eye tracking tool that is typically used for studying eye movement in programming, called eye trace. Therefore, we had to come up with a creative tool that would allow us to create areas of interest around important components of the code, so we could monitor how much time people are spending on each type of basically code element. Also, from the codes that we've collected from the participants, we could do static code analysis to take a look at the amount of code that they wrote, the complexity of the code, how maintainable was that code, the vocabulary, volume, and difficulty, and how many coding style errors they made per line of code, which is another indicator of code quality. So the static code analysis results suggest that basically for the Copilot group, people wrote more code. Some people wrote a lot more. So almost some people wrote double when they were a driver, but not all of them, not all of them that made it statistically insignificant. So some people elevated the average, but not on a statistically significant level. The only metric that seemed to be statistically significant here is the Halstead difficulty, which indicates that the code generated with Copilot was slightly higher complexity, higher difficulty to comprehend than code generated by human pair programmers. Nonetheless, none of the metrics showed a significant difference between using Copilot and a human pair programming. We also took the same snippets of code. We removed any indication of where this code came from, and we gave it to human evaluators to annotate it. And we told them, can you evaluate the readability of this code? And we gave them metrics to think about in terms of readability, like adherence to coding style, a ratio of comments to code, selection of good variable names, and so on. And the human evaluators gave their scores without knowing where the code came from. And when we analyzed the results, we also found that the readability scores that were given by human experts to the Copilot, navigator, and driver sessions were also comparable. They were not statistically significant from one another. So that kind of gives an indication. Although the Copilot code received higher variation in the readability assessment, the median actually was all identical to the driver navigator almost. So this is interesting that the code itself is actually very, very similar to human written code. So where does the problem come from? So the problem comes from the fact that people actually did not spend enough time on the code to read it. So while they were inspecting these suggestions, they were actually not doing much inspection. They were actually reading a tiny bit of the code. It looks correct, so they would accept it. And the difference was huge in eye movement. So the eye tracking methodology allowed us to find that actually people differed significantly between the Copilot group and whether they were actually collaborating with a human. With a human, they applied better scrutiny, better inspection, better reading of that code. That is an important result. So basically, the results suggest that programmers make fewer fixations and spend less time, which is an indicator, again, of automation bias. What we would gain from a result like this is that we will need to tell students and programmers to be aware of the fact that AI-generated code is similar, if not less quality than human-generated code, and therefore it requires higher level of inspection, not less. And we need to tell them about the idea of automation bias, so they would actually be aware of these defects that are actually very, very expensive to fix later on. In the same realm of basically linguistic factors in source code, I picked a sample for a project that talks about a lexical similarity in identifier names. So there's something called linguistic anti-patterns, which are basically typical names or typical behaviors that programmers do that result in lowering the quality of the code and creating problems that would make comprehending that code, understanding it harder. So set reshuffle cutoff set method that returns is one example of that. But we focused on a small category here, which basically relates to the idea of lexical access. So whenever we're reading a text or source code, we're trying to retrieve three things, three pieces of information from the actual shapes that we see in the word itself, or shapes of the letters in it. The first dimension is orthographic, which is basically the word form. What does this word look like? The phonology, which is basically the pronunciation of the word, and semantics, the meaning of the word. And of course, the goal when we are reading is to figure out the meaning so we could actually connect it to a representation that we could match to background knowledge and we could understand whatever we're reading. So the goal is to try and see, in the way that we pick variable names, especially common variable names, are we making any violations or issues that would make reading the code harder? So we study this on orthographic level, and here I have an example. So programmers use I and J in the same scope a lot for nested loops. This comes from programming languages that are no longer in circulation, where a variable like I and J were automatically integers, and it kind of made it a little bit easier to write code that way. But we still have this relic that we keep to this day and possibly continue to teach our students. But I and J are orthographically, in the way that they are shaped, are very similar. So we wanted to know if this could actually create problems in basically how we analyze or understand the code. Similarly, phonological similarity talks about similarity in the pronunciation. So a variable like write and right, as in writing. Here we have like right as in correct or left and right. They have the same pronunciation, and we wanted to know if this actually hinders comprehension if two variables have similar pronunciation in the same scope. And the last dimension is semantically. So if I have something like count and total, semantically they are very close to each other. So would actually having count and total in the same scope hinder comprehension in a meaningful way that we could gain an insight that we probably need a tool that will check this, and we probably should train programmers not to use I and J anymore. So a previous study by Aman et al. Created a large-scale investigation of basically similarity on the dimension of basically orthographic similarity only, and realized that actually these compound variable names that are similar orthographically actually do occur to a decent amount, about 0.5%, which is, I know it's very small, but if you think about debugging for a few hours and then realizing that you placed an I instead of a J, it actually makes a difference, potentially. So we wanted to investigate how much of a difference it makes. Can this form of lexical similarity actually hinder code comprehension? And we wanted to do it in a controlled experiment. So we had an experiment with 31 participants, and they had varying levels of familiarity with Java. And we gave them $15 gift card to participate in an hour-long experiment where they debugged different pieces of code in a realistic environment, which was VS Code, and basically in the Java language. Some of the samples were classical, like I and J in the same scope, basically. And another group, so this would be the orthographic similarity group, and another control group would be the dissimilar group, which would use names that are not similar orthographically, like row and column, which would be more meaningful, better names that adhere to coding style rules. Something like write and write, and the control group would have something like postfix and write. The rest of the code is identical, the bug is identical, and the people had to perform exactly the same task. And for the semantic similarity group, they had something like count and number, which are semantically close to each other, but not necessarily identical. And another group had iteration and side up, which are dissimilar semantically. They are not similar to each other. So the interesting results, at least for the advanced programmers, is that when we had orthographic similarity, people were actually less successful in actually finding the bug and fixing it, despite the fact that they were advanced programmers. And with phonological similarity, we see the same pattern. For semantic similarity, it seemed like it didn't actually make a difference. And possibly that's because it's a latent stage in the comprehension process. Similarly, if we look at the duration it took people to find the bug, previously we looked about how successful were they were actually able to find the bug within the 10 minutes that they were given for the bug, or 15 minutes. In terms of the duration, we find that the dissimilar variables, when we gave the good names that did not have that similarity problem, people were consistently able to find the bug faster, even in the semantic group, which didn't show an effect for success, but it showed an effect for the duration. In conclusion, basically, we created a tool called Namesake. It's an experimental tool. You can find it on GitHub. It's open source, and it's just a demonstration for this idea that allows us to scan any piece of code and find problematic variable names. Of course, this code was intentionally designed in a way that we would have something like E and F. They are actually similar orthographically, and write and write. And it catches these similarities to a really good accuracy level, I think in the low 90s when we match it to human examiners. But it also affirms some of the rules that we know about coding styles, such as don't use a single character variable name, which is a really good rule because single characters are easily confused for one another. I think somebody has their hand up, so I'm gonna pause here and let anybody ask a question.
Hey, can you unmute the person who asked this question, please?
I cannot see the
Message, there is a question in the
All right, apologize about that. If there is no question, I could keep going. We'll keep the questions near the end.
Hey, Naser, there's a question in the chat. Can you please see that and answer?
Yep. Sorry, let me check it. Okay, I'll read the question. I think how much variation is there between people and your tracking results? I suspect that dyslexic people do eye tracking much differently. I have a time conflict. So, okay. So it's a really good observation about dyslexia. So the participants that we get in our experiment, they are normal vision, and we, look for participants who do not have dyslexia, although we are interested in dyslexia in other projects. But it definitely plays a role if the participant had a non-normal vision or had a vision problem that affected their ability to read. But dyslexia is an important one for sure. It's an excellent question. In the possibly last 5 minutes, I want to talk about another dimension that is made harder by basically eye tracking with code and in the context of reading in general. So can we make eye tracking more accurate and more affordable? So the eye tracker that I showed you earlier cost tens of thousands of dollars, approximately $30,000. And not everybody can afford that, especially if they are not thinking about it in the context of research, but they want to actually use it in a practical user interface way. So one of the problems that we find a lot in eye tracking studies, even with very high accuracy, very expensive eye trackers, is called drift, where the eye movement drift from the actual fixation position due to inaccuracy in either calibration degradation over time or change in lighting or the participant moving during the experiment, which would make the eye tracking data look something like this. So in certain parts, actually very aligned with the text, but at certain times we have a small drift here that moves the fixation from their intended words. So this problem is harder and more difficult when we read source code, because unlike a natural language here where people read in this linear pattern, when we read code, we actually read it in a non-linear way. In other words, we jump from one place to another. We do these progressions, jump forward, and we also read things, realize, oh, I need to go back and take a look at the signature of that function or method. So I jump back. And these jumps forward and back create a pattern that actually violates some of the assumptions that are made by the eye tracking correction algorithms. And I'm going to go over this somewhat quickly. So we have different patterns of this drift. Sometimes it's noise, where it just purely drifts from the word in no particular pattern, just up and down, no control over it. Sometimes it's a stope, where we have one side has a lot of drift and one side is actually correct. Sometimes the beginning of the trial is correct, and then at the end we have the last line we have, or as we go down, we progressively have more drift. Offset, all of the fixations could be moved on the X or Y dimension, just purely a calibration error. And we have two patterns that are not necessarily distortions, but these are reading patterns that are nonlinear, similar to what we would see with code. Regression is one of them, where we jump back to reread something that we've read earlier. And progression is another, where we make jump forwards. So these patterns make the correction process of trying to overcome this drift algorithmically harder. So there are so many automated algorithms to correct for drift. I'm going to mention a couple of notable ones. Warp is an extremely excellent algorithm, but it makes an assumption that reading is linear, in other words, from left to right and from top to bottom, and it's based on the dynamic time warp algorithm. Hybrid algorithms usually they use warp, and they try to figure out when a regression happens, when a violation of the linearity assumption happens, and they split the fixations so they would be corrected in something other than warp. So hybrid algorithms combine warp with something with another algorithm to just allow for regressions to happen. And some of the simple algorithms like attach and chain, they are actually very simple, and they do not make assumptions about the data. Their accuracy tends to vary a lot, but they are actually very simple algorithms where we snap the fixation to the closest line. So the observation that we've seen in previous research is that no single eye tracking correction algorithm is universally effective across reading patterns and distortions. Each algorithm seems to be suitable for one pattern. So in this project, we created an adaptive approach. So in other words, we scan the trial, and then we automatically decide what algorithm we're going to use based on the pattern that we see in the trial, instead of correcting the entire data set with one algorithm. And this allows us to look for patterns like linearity. Is this linear reading? we could use warp. It's an excellent algorithm when we have linear reading. If it's nonlinear, we're going to take a look at what kind of nonlinearity do we have. Do we have regressions? If we have regressions, we use hybrid algorithms. If we have both regressions and progressions, then we're going to use a simple algorithm such as attach, because we cannot make a lot of assumptions about the data. So this idea of adaptive correction, we could assess it on simulated data, and I'm going to show you the results. Basically, we generate trials that are computationally generated. They look correct initially. We introduce different types of distortions and regressions and progressions to them, so it would be incorrect. And then we would correct it with an algorithm, and we would compare the correction to the original. And that would give us the accuracy of the algorithm, especially when we run it on a large set of simulated trials. So here are the algorithms, and here are the patterns on top. So we have two big patterns. These are distortions, and these are nonlinear reading. And this is the mean accuracy. And each cell basically tells us the accuracy. For example, cluster, when we have noise, how does it perform overall? We can find a few patterns in this figure, which is basically ranked the best algorithms that are at the bottom. So the first observation is, again, algorithms make a trade-off between distortion and regression. Algorithms that perform really well with forms of distortion, they don't perform very well with regression, and algorithms that perform very well with nonlinear reading, they actually perform poorly or less than perfect when we have distortion. Hybrid algorithms that were intentionally created to allow something like warp to work with regressions, they actually handle regression very well, but progressions are a problem, less than perfect. And adaptive algorithms, this idea of scanning the trial and then determining which algorithm to work, to choose, seems to work really well across the board. At least with simulated data, it seems to be very, very accurate. But before we celebrate about like 99% accuracy, if we try it with realistic data, so if we have real data from 4 data sets that combine natural language of English, Italian, Java source code, Spanish, Chinese, Hindi, Russian, Japanese, Kazakh, Urdu, and Vietnamese, in addition to poetry in English. It's a very diverse collection of data sets, so they will give us different reading patterns. Some are linear, some are not. We can see that basically ranking the algorithms, once again, adaptive algorithms perform really well, better than a single algorithm, but also we can notice that the performance is not that great. The best algorithm is in the 86% accuracy range. Hybrid algorithms are decent, but it's still an open problem. Simple algorithms like attach and chain seem to actually work very well with this kind of diverse dataset environment because, again, they make very few assumptions about what kind of trial we're dealing with. So I want to end my talk by thanking students and collaborators. There are so many to mention by name, but without their effort, none of this research would be possible. And I want to thank you all for listening, and I look forward to receiving your questions.
Naser, thank you, Naser. I will unmute all the participants right now. And if anybody wants to have any questions.
I think Michael says that they cannot unmute.
Yeah, I'm just... Michael, can you please try again?
Yes, it did work. Thank you.
You're welcome.
And so I wonder if you looked at all, Dr. Al Madi, am I saying that right?
Yes.
At amblyopia as well, the people that have one eye that's stronger than the other and may even switch between eyes. So you're only tracking one eye for all of this, right?
Yeah, so with the typical eye tracking, we look at the dominant eye, which is usually the right eye for people. But sometimes while we are setting up the eye tracker and the calibration, we realize that the left eye is the more accurately tracked one, so we track the left eye. Although the eye tracker itself is able to track both eyes, that opens the door for problems such as the one that you just described, where we could have the two eyes are not actually correlated, perfectly to a single word, and that kind of makes our job of determining where this person is looking at harder. But
Okay.
we did not consider it, and I know that there are many conditions such as like hemianopia, for example, where we can have like a reduced visual field, which would make eye tracking experiments significantly harder. So for a controlled experiment, we look for normal vision or corrected to normal. So if somebody wears contact lenses, we could actually include them in the experiment. But usually things like glasses and vision problems, they could either be very hard to track with an eye tracker, or they would actually violate, the generalizability of the results. So we look for normal or corrected vision people. That's an excellent observation.
Good. Yes, thank you. Thank you very
Thank you.
much.
Yeah, thank you.
Yeah,
Let me throw one in. Do I get extra credit for finding 2 typos in your slides?
Please, I I appreciate it.
I'll is your email somewhere?
Yeah.
Oh,
Actually, the next slide. So you could find me on LinkedIn. I'd appreciate, um, connecting with people. And here's my email address as well. And thanks in
okay.
advance.
Got it. Thanks.
Dr. Madi, in your
Yes.
project, did you consider people using the diversity, meaning to say, like, a particular group of people from particular countries have different mindsets of looking at the content or reading the content?
Yeah, that's actually a very cool idea. One of the data sets that I mentioned, which is the multilingual eye tracking data set, multilingual eye track data set, we created it, and it's the one that includes all of these languages. So we looked at languages that are underrepresented in research. Almost all of the research in basically natural language eye tracking is in English. There's so much research that kind of studies the English language. And every language gives us a unique perspective about what's going on in the cognitive system in the brain. So, or like in human cognition in general. Each language is unique in a different way that actually reveals something about how the human brain works. So we wanted to create a data set that would allow us to see these differences, and it would include languages that are rarely studied in research, put them all in a single data set. And I think in the MET data set, we have something like, if I remember correctly, 60 different participants who are multilingual. So they speak English or they read English and they read something else. Some of their other languages other than English, they speak it natively. So it kind of gives us a perspective as well as about like multilingual brain. And also some of the people are actually learned it as a second language. So this is some of the only data that we have for languages such as Vietnamese, for example. To the best of our knowledge, or at the time of publishing this data set, there were no eye tracking studies in Vietnamese. Similar for Urdu, Kazakh, Japanese, and so on. And some of the different perspectives that we could see, such as like reading from right to left or left to right, such as Urdu, for example, how does that influence when the same person reads English? Is there like a spillover effect where, because they read from right to left a lot, would their fixation position be different when they read English because their neural network is trained in a different way? So these kind of questions can be explored with the MET dataset. It's not yet fully collected, so we are actually still collecting more data for the MET dataset too. include more people and be able to come up with better generalized results. But the data is already publicly available, what's collected so far, and any researcher anywhere or anybody who wants to take a look at it, they could actually find it under the Fixate tool. So there's a tool called Fixate that already includes this data set.
Thank you.
Yeah, thank you.
Nasir, I also have a couple of questions.
Sure.
Yeah. So as you were saying, you did some analysis on GitHub Copilot that
Yeah.
writes the code and everything, right? So I've also started incorporating AI into my workflow for in programming and everything.
Yeah.
And what is one big thing that developers make that harms the code readability? I mean, you said when we do the analysis between the GitHub Copilot, the AI programmer versus the pair programmer, or the human. So like I've seen you're saying that the human readability is more in the human aspect who are writing the code rather than the AI generated code.
Yeah.
And a lot of times as developers, we try to not do a lot of commenting, or we try to skip a lot of those if there's a POC kind of a thing that we are working on a limited time. We try to do things so fast, and because of the requirement gap that we have, or the expectations that we have, we try to do it fast. And what is that one thing that harms the code readability? That's what my question is.
Yeah, so good question. So I'm definitely not against AI. And if there's like anything that we learned from this study, which was done early on, like people were actually still new to like AI generated code, is that the AI generated code was actually decent. It was very comparable to human written code, which human written code also has the potential to, include bugs and so on. And that's why we encourage people to inspect it. So the fact that it's AI generated doesn't mean that it's better. It's just similar to human written code. And therefore, we still need to inspect it to actually see if there are some bugs in it, some problems in the code, and we could probably fix them after we accept, or we look for another piece of generated code to accept it. I think AI generated code has been really good at making programmers more productive. But the question in the context of this figure that I showed earlier is, are we actually trading like short-term gain in making coding faster by also including bugs that are hard to find that will be very costly to fix during production? So that's one question that will require some years for us to be able to look at like code repositories and answer. But if programmers are able to use AI and they inspect the code and they think about the quality of the code, specifically in how they name identifiers, not writing too much code, like the best code that you could write is not writing the code at all. Like if you could actually remove code, that would be an awesome contribution. So if you can get the same functionality by less code, that would be great, as long as you keep the code easy to understand and write. And sometimes AI generates code that is clunky, that is not necessarily clean as we would hope AI to do. So keeping that in mind is an important factor in how we use AI to be more productive. But definitely, by all means, we should learn how to use AI to help us in programming.
Yeah. Thank you.
Thank you. Yeah.
The time is actually 6:59. If anybody has still any questions, we still have a minute left. Yeah. I saw around 18 people joined, and some of the people have dropped. But that's fine. So yeah, I just want to conclude this session. Thank you so much, Nasir.
Thank
for
you.
your
Thank you
answer.
for the invitation.
Yeah, it was a brilliant talk, and you have given us a new lens through which we can view the code we write and read every day, and how important it is to write a good code. Um, and
I
once again,
appreciate it.
yeah, big thank you for
Thanks.
all our audience. Your excellent questions made this even more enriching and much more good discussion. So we appreciate your time spending with us in this evening, and we hope to see you in the next time. We'll be posting this video on IEEE Schenectady section, and also we'll be putting on the link on the IEEE Schenectady website as well. And we are continuing to do these events. We have one more event coming on October 29th by Professor G. He's working at RPI. So our section chair, Mr. Lalit, has organize that. So we'll be seeing everyone over there. And thank you, Nasir, once again for all
Thank
your.
you.
Thank
Thank
you
you, John.
for
Thanks for organizer and the audience. I really appreciate it. It was a
Thank
pleasure.
you. Have a good day.
thank
Have a
you.
good night. Thanks so much.
Night.